Okay, back to business. All right, so we've got diabetes and it looks like level of education, right? So is there some correlation between diabetes and level of education, or are these independent variables? All right, so null and alternative hypothesis. So the null hypothesis is that they're going to be associated or not associated? Not associated. This will always be our null hypothesis. And then the alternative would be that there is an association. So I think that's C. The two variables are not associated. The two variables are associated. I think that's C. Oh, so it was because you just get one shot at a multiple choice. Is that right? Oh, there's more to it. Okay, good. The test statistic. Okay, so that's our chi-squared value. This chi-squared value that reflects what's going on in this table. And remember, the bigger the chi-squared value will tell us what about the two variables. If it's larger, chi-squared is larger, then more indication of not independent or independent. Not associated or associated. If the chi-squared value is bigger. He's saying associated. Agree with that? Yeah, the bigger the chi-squared value is, the more indication that the variables are associated. Knowing one changes what you would think about the other, right? Changes what you would think about the other variable. Okay, so we're going to go to StatCrunch. Okay, and so here's our data, and we know that we're going to do a table, right? Stat, table, contingency, with summary, right? This is the summary data. And our columns are going to be
2, 3, 4, and 5.
Yep, 2 looks like it. 2 through 5. All right, the row labels are in 1. Column 1. Column labels are not in any row, so we'll just leave it blank. All right, we're going to we want the expected count, and then we want the chi-square test for independence. So it reprints, it gives the table, and then gives what would be expected. Remember how to find those? What would be expected if they were totally unassociated, right? Totally not associated. What would you expect for these counts? And remember what we did was we got, what did we do to do that? We took 109, what percent of, how did we do that again? 109. Right, so we took 109 out of 2380. We got the total diabetes percent out of that. And then we said that all of these, or no, we did this. We did 558 out of 2380 for this variable. And then we said all of these percents should be that same percent of their respective groups. If that percent doesn't change down the board, then there's no association. Okay, and so why is there 6 degrees of freedom? Because we got, oh wait a sec, something's not right.
It's because you multiply it.
You multiply
109 times 558.
So you get 4 and 3, and then you just minus 1 from each one.
No, but this table isn't right because it's taking these totals and then making a total of the totals. That's what I'm looking at. Shouldn't this be the bottom row?
Yes. You have to delete the
Yeah.
total row from the
You highlighted
spreadsheet.
Yeah, so something, this isn't right. Because this is supposed to be the total of these two, and then it did another total row, so we did something wrong. Let's try again. Okay, so we got to get this out of here. We got to get this total row out of here because it's going to do it for us. So we'll clear that row. didn't work. That didn't work. Anyway, we'll just delete these out. Okay, now let's try it. So when you're using the technology, you have to be aware and notice stuff like that. Maybe that could have been why we had some difficulty on this one. So tables, contingent. With summary. Okay, yeah, so it's going to just take all the rows. So if StatCrunch gave us a total row, then it's not going to know that. It's just going to think that's a third row of data. Okay, and that's what it did. So we got to get that out of there first, like I did. So it was 2 through 5, is that right?
Mm-hmm.
But was 5 the totals, or was that 6 was the totals and 5 was the data? Okay. So row labels is variable 1, and then expected count, chi-square test. Okay, this is better. See the difference? So it didn't know that there was it just thought that was another row of data, and it made its own total column, including the total row, so that's not going to give us the right results. Okay? So we want this to be the data here, and now, what's our degrees of freedom? 3 times 1. That's right, 3. Okay, so we gave our test statistic 22.6. 22.6. Oh, 3 decimal places? Thanks. 609. Okay, p-value, it tells us. And what is the p-value? That's area under the curve. That's probability of making a type 1 error. Is 1 the third decimal place? No. So to 3 decimal places, it's 0, right? I think. Yeah. So what does that mean? That means that's a teeny little amount of area that we've got for the p-value. So what are we looking at here? So we've got our test statistic out here, say at 22.6. And what does that p-value represent? It represents this area to the right, the probability of making a type 1 error. And what was that again? Relating to making conclusions about our hypotheses. Remember what a type 1 error was? What's that? Rejecting when we shouldn't have. She's guessing that it's rejecting when we shouldn't have. Agree or not? Type 1 error. Well, what area is this over here? That's the rejection region, right? So if we're over here, we would reject or not? We would reject. So she's got it right. It's probably the type 1 error is we reject when we shouldn't have. So what is this indicating? It's saying there's a very low chance of that. And why is that? Why is there a very low chance that we would reject incorrectly? Yeah, because the test statistic is so high, right? We're way out here indicating association or non-association. Indicating strong association, right? Strong association, so that if we were to say, yeah, these are associated, we'd be a very low chance of being wrong, right? Why? Because that test statistic is so high. All right, what about the, we didn't ever do a critical value, though. So we need to get the critical value. So 1% significance level, how many degrees of freedom was it? 3. So find that critical value. 3 degrees of freedom and 1% significance. As soon as you get it, shout it out. 11.3 something?
Yeah.
So that is what p-value is associated with the critical value. What's this area? All of that to the right of the critical value. How much area is that? This doesn't stick easily. Yes. How much area is that? Remember, this is what? What does it say at the top of the thing? Doesn't it say chi-squared alpha? Is that what it says? At the top of your chart? So what area is this? 1%. 1%. 0.01. That's what alpha is. Alpha is the probability of making a type 1 error for that particular critical value. That's alpha. Alpha is an area, right? Alpha is an area. It's the area or probability of a type 1 error given for a particular critical value. So we started by saying we want a 1% chance of making a type 1 error. That's what the problem gives us. 1% significance level is the same as probability of making a type 1 error. That's alpha. And from that, we get a critical value, right? The critical value is determined by how much error are we allowed to tolerate. We're saying we're comfortable tolerating a 1% error, meaning 1 out of 100 times we would reject incorrectly, right? 1 out of 100 times we would reject incorrectly. That's how certain we want to be. 1 out of 100. But then the actual test statistic was way out here, saying no problem with that. The chances of you now that you've rejected incorrectly are like minuscule, like almost 0. So this is actually in these problems when they give you the significance level, they're saying this is the type 1 error the percent of the time we're willing to tolerate to do this test. 1% means 1%. We're willing to say 1% of the time we'll get this wrong if we reject. And that's what gives us our critical value. Okay. So significance level, alpha, area under the curve for a type 1 error are all the same thing. Okay. So what are we going to do? Reject or do not reject? Reject. Because the data do provide evidence or don't provide sufficient evidence? We always reject because there is some evidence. We reject always because there's some evidence to suggest an association. No, I didn't want to do that. Okay, questions on this? Questions on this problem? That was a good one. It covered lots of ground. So maybe it was the difficulty, the StatCrunch thing, not noticing that it took the total and made it the third line of data. So you got to be careful when you use technology. You have to be. So technology is wonderful, does great things for us, but we have to be efficient managers of it, right? That's a good takeaway there. Okay. So notice make sure you're doing it right. Okay. Other one was
Number 8.
in the second set, right? Chapter 4 set.
That was the second one.
Oh, I think this is number 8. Is this, yeah, homework number 1. Okay. So we have. Okay, so we have the age and price for 8 randomly selected ambulances between 1 and 6 years old. X denotes age in years, and Y denotes price, hundreds of dollars is information. Okay, regression equation. So we know that that's we talked about that. To actually get that is a long and tedious computational problem. We want to use StatCrunch to do it for us. Okay, so we want a linear regression for this data. So we go stat, and we go goodness of fit. No, we do what is that? Regression, simple linear. The x variable we want is column 1, which they called x for us. That's nice. Column 2, which they called y for us. We don't care about hypothesis, any of that right now. We just want a fitted line plot. That's all we need for now. Okay, so it looks like 427, how many decimal places? 2. 427.58 minus 27.83. Remember that. 427.58 negative 83.
83.
And x is already there. Okay, so a couple things to notice there. It's they're putting it in the form of plus. So we have to get that minus sign in there with our answer. Okay, and they've already put the x in there for us. So they're just looking for the b0 and the b1, right? So this is what the initial intercept, the y-intercept, or where we'd expect y to be when x was what? 0, right? This is what we expect y to be when x is 0. And then this is what the rate of change. For a unit change in x, how much does y change, right? For a unit change in x, how much does y change? Okay, so noticing, so what does this tell us about the regression line that has a negative rate of change? What will we know about the regression line?
It's going to be a down slope.
Downward slope. So just from that right alone, we can eliminate B and D. And then we have to kind of plot a few points here. It looks like at 6, there's a 255 and a 7. Are there 3? There's 3 6s. 370, 216, 2. It looks looking like this one over here. Because look at x equals 6, you've got these 3 kind of different data points. Here it's showing they're all kind of the same. But they're quite different, right? They're almost 100 different. They are 100 different. 110 different. So I'm looking at, for x equals 6, I'm seeing these 3 points right here matching up with these 3 data points here. Understand that? Makes sense? Oh. What's that? I thought it was 3 something. Am I misreading it? Oh, I saw this. I saw the 350. So you got to, so read carefully. 260, 255, right. So those are all close together. I was looking at this one here. I kept looking at this one. Yeah, so 260, 255, 270, close together. This one here. Okay. So there's 3 parts remaining here. How do I keep going? Oh, here. Describe the apparent relationship between the 2 variables. Price tends to decrease as age increases, increase, remains constant. There's no apparent relationship. So we're looking at this. Price tends to do what as age increases? Decrease, of course, right? It's going down. That's our negative rate of change. Predictor and response variables. So remember, the predictor is our independent or our horizontal axis variable. Response is the dependent or the vertical axis. So predictor will be age, and response will be price.
C.
Okay, outliers and potential influential observations. So an influential observation would be one that we would take away, and it would have an influence, have a significant influence on the regression line that we would get. So looking at this plot here, is there any that we would take away and say, oh, that line will change a lot if we take that one data point away. Not really, right? Not really. And there's certainly no outliers would be ones that are like, okay, this is just a mistake in the data. Like it just doesn't belong. Okay, that's an outlier. So to me, I'm thinking there's neither in this case. No outliers and no influential observations. That's what I think. Okay, questions on this problem? Oh, there's still another one. Predict the value of the response for a 3-year-old ambulance. So this is what a regression line does. It allows us to, so we don't have data for a 3-year-old ambulance, right? We have 1, 2, 4, and 6, and 5, 1, 2, 4, 5, and 6. But we don't have 3, but the line then can give us other points like 3. So we're going to plug 3 in for x, and it'll give us the corresponding value of the point on the line that predicts what the price will be for 3 years. Someone crank that out. 27.58 minus 27.83 times 3. As soon as you get it, tell me. Yeah, that sounds about right. Right. So here's 300, 400, like 344. That could be right. Someone else get that? You got 344 point.
There's 100, so we have to times that by 100. So
No, it's dollars. 09?
34,409.
Oh, this is in hundreds of dollars, and it's asking for a price. Okay.
Granted, then there's $100 is needed.
So these prices are in hundreds of dollars. So, for instance, this is a $27,000 ambulance. Okay, and this just says in dollars. So you're right. So we're going to go 09. But round to the nearest $100. So rounding to the nearest $100 would be 3400. That's a little tricky because you got two things going on there. You have to realize that these ambulances are $100, so you have to multiply by 100. But then they're telling you to round to the nearest $100. So I think it's 34,400 because that's to the nearest 100. So there's kind of two things you have to deal with there in that last question that might have been a little tricky. Does that make sense? So make sure you know what your variable is. This is not the cost of the ambulances, right? This is in hundreds. So you have to, so this is talking about a $27,000 ambulance, a $42,000 ambulance. And then that question is saying round to the nearest 100. So you're going to have zeros in the 10, the ones in tens place. Okay, questions on that example? Okay, so we have just one topic left, and that's continuing on with regression, this linear regression. So we're going to have exam 3 next week, and then we didn't say there was going to be a final, but what I'll do is we'll introduce an optional final to replace one of your exams if you want to do that. Okay, and that'll be during the regular scheduled final time. Okay, but if you like your grade after you take next week's third test, like I promised in the syllabus, that can determine your grade in the class. But then you don't drop a test. You're taking your 3 tests already. But the final then would be cumulative. It's going to be you have to do everything again. Yeah.
With the final, say we just like bomb it or something, would you just drop the final then?
Yeah, I dropped of your 4 exams. I dropped the lowest. But you're not going to bomb the final. I know.
Will we know our grade before?
Yeah, of course. Of course. Okay. So we got this last thing to do here, which is diving deeper into the regression idea. So where were we? What's that?
What day next week will the test be?
Well, I don't know. It depends kind of how far we get today. So we'll just hold that off. So of course, either Monday or Wednesday. But we'll see if we can. If we're comfortable with everything we do today, then we've got all day Wednesday to review. Then we could do it Monday, and that would be the last day. Then we wouldn't have that would be the last day of class. But it might be wiser to, review all this stuff Wednesday and then have another review on Monday for the exam Wednesday. We'll see. We'll see what's best, and we can take a vote if you guys want to vote on it. Okay. My experience is that rushing through things is not good for your grades, like good for your understanding of things. So I don't want to make that mistake. Okay, so the next thing we're doing is we're going to section 4.3, and we'll talk about what's called the coefficient of determination. Okay, so we're dealing with two variables at once, right? Two variables at once. Age of the ambulance and price of the ambulance. What was another one we saw earlier? We saw educational level and diabetes, right? Diabetes and education. So we're looking at two variables together. That's what the independence test was looking at, and now this is what also the regression stuff is looking at. So when we talk about this variable, whatever it is, this y variable, we're saying, what's the best predictor of it? Is it the x variable? Meaning, is there a high degree of correlation? If you knew what x is, would that help you determine what y is? Or if they're not associated, then how could we predict what y is? We'd only just have the mean of y, right? We just take the average of y, and that's what we said all semester long, right? That the average is like typical value, or indicative of what the values are like. So if there's no association between the two variables, we're not going to pay attention to x, and the only thing we've got to know what y is like is the average. Does it make sense? So these are like, so does knowing x help us to find y, or is it just kind of like y bar, right? Y bar is the mean. This is not a regression line. This is just, I'm just showing you like maybe what the mean value of the data is. So for this scatter plot, would you say it's better just to predict y using the mean of y, or is it better to actually look at x in order to try to predict y? What would you say for this scatter plot? Is there a correlation between x and y that's worth looking at in order to predict y? Or is just the one value of the mean the best predictor we've got of y? What would you say? Any degree of correlation or not?
I'd say there's a degree of correlation.
Yeah. So when x is lower, what are we going to say about y? It's below the mean, right? So it is lower. And when x is a little higher, we can safely say that probably y is going to be higher than the mean. So that for this particular example of the scatter plot, we want to consider correlation. We want to use x to predict y because there's some. It looks like there'd be some best fit line here. I'm going to try it again. That's better. There is some correlation between x and y. When x is a lower value, we want to use that for information because y is lower. And when x is bigger, y is bigger. Now, is there strong correlation between x and y? No, right? There's some significance. That's what we're talking about today. So there's some significant difference between some of the data and this best fit line. So it's not a strong correlation, but using x to predict y is certainly better than just using the mean of y to predict y. Do you see that? For this particular data set. But x is not a perfect predictor of y, right? X is not perfect. Okay, so here's how this works out. This is the mean of all the data, right? We said that's one possible predictor of the y variable. This is the mean. Mean of all the observed values, okay? this is a particular observed value, right? So this we're looking at, we're just focusing in on at a particular x value, we got an observation here. Okay? We got this observation right here. So that's the observed value. Here's the mean of all the observed values down here. Okay? So that is one way of predicting what we would get. Okay? And then if we made a regression line out of all the data, this y value is right here is the what we would predict from the regression line for that x1. Okay, so there's the true data value, there's what the regression line would predict, and then there's what the mean would predict for the value of y. That's what we were just talking about, right? That there's two ways to predict a value of y, or say what should y be at a particular x value. Just the mean of all the data, or the regression line value, the y hat, what you'd get if you plugged x1 into the regression line. Okay, so this right here, this distance right here, is deviation explained by regression. Okay, so this is the mean of all the data. This is what the regression line would predict. So the difference between those two, that distance, is deviation that's due to the regression. That's called the SSR. So this is called the SSR. The sum of squares due to regression. The sum of squares due to regression. Okay? The variation in the observed values of the response variable explained by the regression. So it's how far the regression is away from the mean for a particular x value. Or for all the x, so it's a sum. So it's for all the x values. Okay? Then, deviation not explained by the regression is just the error, right? So it's the error of the regression from the actual data point. That's called the SSE. Right, so this is having to do with how close are our data points to our regression line, right? How close are our data points to our regression line? If they're close, then the error is small. But like in that last picture I showed you, there was some significant error between the data points and the best fit line, because not all the data points are close to the line. Okay, so that's a matter of the SSE. And so then the sum of all that error is the SSE, error, the sum of squares. So then the total sum of squared SST is the total of the SSR and the SSE. And so that's how far, total error. So it'd be how far the data point is away from the mean. How far the data point is away from the mean. So there's lots to attend to here. There's lots to keep track of, but it should make sense. For a particular x value, we're talking about the mean of all the observations as one predictor of y, the regression line, the best fit regression line as a predictor of y, and then the actual observed data value y itself. So the deviation explained by the regression would be the difference between what the regression says and what the mean says. The error would be the difference of the observed value and the regression. And so then the total deviation is the total deviation of the observed from the mean. That's the sum of those two. Anybody have a question? We have to know this. There's questions about this stuff. So we have to understand this. But there's A lot going on. So anybody have a question? Okay, so so when we're answering questions, then we have to know these definitions and we have to know what they mean in order to kind of succeed at answering the questions. All right, so then there's this coefficient of determination. Okay, if you take the SSR, what did we say? The SSR is this one.
The deviation explained by the regression.
Right, how far the predicted value from the regression is from the predicted value from the mean. That's the SSR. If you take that fraction of the total, the SST, you get something called the coefficient of determination, R squared. And so let's think about this. If that was a high percent, so if SSR divided by SST was very high, say close to 1, if that fraction was close to 1, what would it mean about the error? And remember, these are sums, right? This SSR and SST, there are sums for all data points. SSR is the total sum of deviation for all data points, same with SST. So for all data points, if you take SSR divided by SST, and this is, say, high, close to 1, this fraction, what would it indicate about the total error between the data points and the regression line? What would it indicate?
Small.
Small, right? If SSR over SST is almost 1, that means that this is a very small fraction of the SST, right? If this is a big fraction of the SST, then the error part is a small fraction of SST, and that would indicate low error of the data points to the regression line. Low total error. Of data predicting or compared to regression. Okay, we already knew this from before, right? Previous page, we knew that. Okay, but this is the key new point here. That if SSR is a large fraction of SST, that means that SSE is a small fraction of SST, meaning the total sum of error is low. And so then are the observed points all close to the regression line or far away from the regression line? Close or far away? We've got, in the case that SSR over SST is high, close to 1, a high proportion, then is our total, our observed values, are they all like hovering in close to the line? Or are they all kind of more far away from the line? For high, close to 1, SSR over SST. Close or far?
Close to the regression.
Close, right? Error is low. If SSR over SST is high, then error is low, right? If this SSR, a fraction of SST, is close to 1, that means the fraction of the error to the SST is a very low value, and all your observed values are close to your regression line. Okay? When it's low, all right, close to 0, then what does that mean? When this fraction SSR to SST is low, that means that what about the fraction of SSE to SST? Most of this deviation is due to error from the what? From the observed data point to the regression line, and therefore we have lots of total error, or that the points are not all close on the same line. There's lots of deviation of the observed points from the regression line. So we have high error, high total error. So in that case, we're more inclined, the lower closer to 0 is, we're more inclined to use what as a predictor of the y variable. So the lower this value is, r squared, the more inclined we are to use what to predict the y variable. The mean, right? The mean is just the best indicator we have. This data is not doing a good job of giving us a regression line, so we tend more to use the mean to predict y. Whereas if this SSR over SST, this r squared ratio is close to 1, means our error is very low, we want to use x. We want to use x to predict y, because that regression line is good, right? It's very, all the data points are close to that regression line, so we want to use x to predict y. Okay, anybody have a question? Important concepts. Yeah.
R, you said if R is closer to 1, that means we want to use
R squared,
R squared.
okay? If it's close to 1, then what's happening?
There's not a lot of
The deviation explained by the regression is high, and the deviation explained by this error is low. So the sum total of the error between the regression line and the observed points is low, meaning that the points are close to the line, indicating that we want to use the mean or use the x to predict y. Use x. Use x to predict y, because the observed points are doing a very good job making a trend, right? Making a trend that our best fit line is on. So we had that Orion example. And here's looking at the sum of the observed values compared to the mean. They're the same. And here is remember what y hat is. It's the predicted values from the regression. Y hat is predicted by regression line, right? What's y bar? That's the mean. These are, and then y is actual observations of the variable. Got to get our symbol straight. So this right here, the y hat minus y bar, is this related to SSR, SSE, or SST? This column right here. Is this going to be, actually we're going to square it and add them up. Is this the SSR, the SSE, or the SST?
SSR.
He wants SSR. Agree with that? You agree with SSR? Yep, that's right. It's how far there's the total deviation of the regression model, or the best fit line, from the mean. That's the SSR. And so we're going to look at what fraction is that of the SST to figure out what the r squared is, and then this gives us a idea of correlation of how well the data fits the line. Oh, okay, so what were those numbers again? Let's do this here. So this is 82, 85. That's our, what we said, SSR. All right, sorry. All right, so SSR from the previous was
82, 85.
Thank you. 82, 85. Now, what is this? This is the difference of the observations from the mean. Observations So is this the SSE or the SST?
SSE.
Right. So this is the error. This is the error from the best fit line to the actual observations. That's our SSE.
Professor,
Yeah.
Is it the mean? It's not the mean, is it?
No, you're right. Sorry, that's the regression. Sorry. This is the predicted value from the regression. Thank you. Right. So the difference between the observation and the predicted value from the regression is the SSE. Okay, so our SSE is 1423.5. And how do we get the SST? We're going to add those together, and we're going to get
708.5.
So what's this? This is indicated this is the total deviation between what and what? Total deviation between what and what? Right. And we want to ask what fraction of that total is just due to the regression? Right? That's our SSR over SST. So it's going to be 8285 over 9708.5. Tell me what you get. 0.85. So is this a higher, relatively high fraction or proportion, or low fraction or proportion? It's more towards high, right? So high-ish, right? High-ish.
It's closer to 1.
Closer to 1. Certainly much closer to 1. Indicating what? We should use the regression line to predict price, or we should just take the mean of all the prices to predict what we would get?
Use the regression line.
Use the regression line. And if we go back and look at, we have a picture of this data. We can see it in a second. But this is indicating that most of the error or the difference deviation is due to the regression line and not the error, right? The error only accounts for 15% of the deviation, the error in the data points from the regression line. And most of it's due to the fact the regression is different than the mean, indicating that the regression line is a good indicator of price. And so let's go back and look at the picture. Somewhere back here is our Orion. Okay, here it is. So look at the data, look at the points, and look at the best fit line. And what do we get? We got a 0.85 correlation coefficient telling us that, yeah, we should definitely use age to predict price. And do you see that in the green in the data, in the observations? They're pretty close to this line. There's definitely this downward trend that we want to use to predict price. We don't want to predict price just by merely looking at the mean of all the data, which would be about, what, $88,000. The mean would be around here, $7,000 or $8,000 or $9,000. We can do much better if we knew what age was, right? And that's because the observed values are doing a good job forming a line. There's little error, right? There's a little bit of error, but not a great deal of error. And so that's that picture and this correlation coefficient are in line, or agree. They agree. So maybe this other scatter plot that I showed you here, oh, that one, that's the one I want. That might, we said it'd be better to use X to predict Y, but this might have a correlation coefficient more like 0.6, right? Not as good as the Orion example. This data is more scattered away from there's more error. It's more scattered away from the best fit line. So maybe R squared for this is something like I don't know, 0.4 to 0.7 is what I would guess it's in their range. I'm just guessing, okay? Somewhere from 0.4 to 0.7. There is significant correlation, but there's a lot more error due to the observations being away from the line than there was in that Orion example. Okay, any questions?
I have a question.
Yeah, please.
If SSR over SST equals 0.5, does
Yeah.
that mean Y and X have a 1-to-1 ratio?
No, it means that the deviation of the mean of the observed, half of that is coming from the difference in the regression and the mean, and half of it's coming between the regression and the actual observed values. So this might be a 0.5.
Okay.
So it's like there's an equal amount of deviation due to the regression and error. So that's just they're equal.
So you could use either one in that case if you wanted to?
No, you still should use you still want to, like for this one here, you still want to use X. X is a better predictor of Y than the mean is. It's only when you get down to like maybe like 0.2 or 0.1 and you barely have any, anything of a trend at all that you would start talking about, let's use the mean as our best guess to predict the value. Okay, other questions? All right, so let's do an example from let's do some examples from 4.3. Let's go to 89 here. Come on. Okay. Well, 89. This one. Is a student. Okay, so here is a question. I'll show you how. Let's actually do the next one. Let's do 91. Here we go. Okay. More data. That's good. Okay. So it wants us to do the SSR, SSE, and SST. It also tells us that they already told us that the best fit line is -3 plus 1.2x. Okay, so I'm going to show you how StatCrunch can get those values for us. So we're going to do the same thing we did before. Actually, it was all there when we were doing it before. We just didn't know what the stuff meant. So we're going to go to Stat. We're going to go to Regression, Simple Linear. Column 1 is X. That's already labeled as so. And then column 2 is Y. We don't want hypothesis test. Fitted line plot. I think it'll just automatically give it to us. Let's see here. Yeah, here it is. All right, so you're gonna do the same thing you did before. You don't have to add anything new. And now there's some stuff down here that we didn't look at before, but now we know what it means. Okay, so here is SS, right? This is what we want. Model, that means the model is the regression line. So when you see model, what we're modeling the data, right? We're modeling the data, that's the regression line. There's the error, there's the total. Okay? So what? It's these values right here. So SSR is 7.2. The SSE is the 128.8. And the SST is 136. So let's talk about this. Is the observed data on a significant trend here or not? Do we expect all the data points to be close in, hovering close to the best fit line, or scattered away from the best fit line based on these numbers right here? Our SSR is 7.2, our SSE is 128, and our SST is 136. He wants close to the line. Agree with that?
Yes.
She agrees.
Close-ish.
Close-ish.
Yeah, the R square would be
But we're doing SSR over SST, right? Is that going to be a fraction close to 1 or 0? This is close to 0, right? Which means that most of the deviation is due to error, which means our points are not close to the model, right? Most of the deviation is these observations are far away from it. So what is that ratio? Find that ratio. 7.2 divided by 3.6. Okay, 0.05.
253. 053.
And now look at this. So they already gave that to us up there too. Okay, R squared is the 0.053. But it's good to know where it came from, right? We know and understand what it means. So when we plot this data, what are we expecting to see? A line and all the observations close to the line? A line and observations scattered away from the line. Most of the deviation due to the error. But remember those numbers here. Let's see if I can. SST is 136. SSR was 7.2. Thank you. Integer or decimal, do not round. Okay, got it. 128. 0.8. Okay, got it. All right, verify the regression. Does SSE plus SSR equal SST? Yes. Let me make this bigger, sorry. Okay. What was our R squared value? 0.05. How many decimal places? 429? I hope they show us the picture of the data. Okay, the percentage of the variation in observed values of the response variable that is explained by the regression. What's the percentage of variation explained by the regression? What would you put for this? 5.29%. That's what R squared is. It's the percent due to variation due to the regression, right? As opposed to the error. So when it's low, there's lots of error, right? There's lots of error. State how useful the regression equation is for making predictions. Very useful, not very useful, or only somewhat useful. What do you think, Daisy? Very useful. 5.29% is our R squared. What does that mean? Lots of error or not lots of error? Lots of error between the observations and the predicted line. So therefore, the regression equation is useful or not for making predictions? Not useful. Not useful. Lots of you said useful. You see why not? This low correlation. See, it's a coefficient of correlation. It's a coefficient of correlation. So when it's lower, low correlation. When it's higher, higher correlation. Right? When it's higher, that means the deviation is just the deviation from the mean from the regression line, as opposed to the error in the data values. Shoot, they didn't give us a graph. Will this give us a graph? Did the StatCrunch give us a graph? Let's see the graph.
You might be able to see it if you open up an Excel, maybe.
And where's that? This one? No, I think, no, StatCrunch should show it.
Sometimes like there's an error at the bottom of the results, and sometimes if you click it, you'll like the next page.
Wait, if you click graph,
I
maybe.
already did this though. Here's what we got already. Where's StatCrunch? I didn't close it, did I? Where'd it go?
I think that one day you just closed this.
Shoot. There we are. Graph, scatter plot. X, Y. Okay. Here are the points. What do we have? 5% correlation coefficient, right? Point there, point there, point there, a point there. Do you see that there's a very low linear trend of these 4 points? Like, what would you say? You might say, oh, this is an outlier, and it should be like this up here. Or you might say, this is an outlier, and it should be like this. Right? This is just bad, right? There's no... Using X to predict Y is not helpful. That's why you got a very low coefficient correlation. Correlation coefficient, R squared. Okay, let's look at another example. Look at this one. An instructor asked a sample of 8 students to record their study times at the beginning of a course. She then made a table for total hours studied over 2 weeks and a test score at the end of 2 weeks. So what are our variables? Total hours studied, X, and test score. So is there a correlation between total hours studied and test score? So somehow we have to write something down here for... And one behind you, please. Everyone got one? All right, so we don't need all these crazy formulas. StatCrunch is doing the work for us. It's showing you what the formula is for SST and SSR. Okay? Right, so this is the formula for SST. This is the formula for SSR. Yuck, no thanks. But that means we're all the more responsible for understanding and managing things correctly, right? Because we're not getting bogged down in all the computational details. Okay, so we'll just do it. You guys will answer the questions. So we're going to start with StatCrunch. I'm going to open it up in StatCrunch. Again, what's the variable x mean again? Hours studied. Variable y?
Grades.
The result is test score for the student versus. So we hope, if this is a good course, we hope that there's some correlation here, right? The more you study in a well-organized course, the better you're going to do. So we're going to check for that. Okay, so we'll go to stat, and what will we do? Regression, simple linear. Do the same thing you did before, and then that's all the information you need will be there. X and Y. That's all you need to do. X and Y. Fitted line plot. Okay, so question number 1. Go answer. What is the, I think they asked for SST.
185.43.
What is the SST? SST.
244.
Okay, so you're answering on your sheet, right? So I'm not going to tell you if you're right or not. You can discuss with yourselves. So you're answering on your sheet. SST. Just one decimal place. Just round to one decimal place if you need to. What do you guys think it is? Everyone write your answer down?
344.
Is that the class consensus, 344? Okay. Can't change your answer. You can't change your answer. Are we good? Well done. All right. SSR. SSR. What's the SSR? One decimal place. Or, oh, they want two. Sorry, 2 decimal places. SSR. 185.43. Do you guys agree with that? Okay, SSE, and I'm not going to show you the chart. SSE, and I'm not going to show you the results. So what is the SSE? You got to figure it out. Make sure you agree.
Five, six.
You guys agree on the value?
Yeah, 148.
Okay, what'd you guys say?
158.57.
158.57? They're all nodding. Okay. Compute the coefficient of determination. Go. What's the coefficient of, is that what we called it? Of determination, I said correlation. Termination.
Yeah. And it says 4, so I just put the 0 then. And it says 4 decimal places, but
Because you subtract it, get the, yeah, that's how you, yeah. That's how you do it. Does that add up to SST? Or does that add up to equal SST? Yeah, that's complicated.
Okay, what'd you guys get? 4 decimal places.
0.5390.
Point
5390.
5390. Is that what you guys got? People are nodding. Okay, cool. And what's the percentage of variation due to the regression? What is it?
53.9.
They're saying 53.9. That's it. That's what that core. 53.9% of the deviation is due to the regression from the mean. And then what? The rest, what, 46.1% is due to error, right? 46.1% of the deviation is due to the error from the observed values to the regression. Bless you. Okay, so low usefulness or moderate to high usefulness of the regression line to predict test score. So predicting test score from study habits. The regression line not really useful or moderately to high usefulness. It's like moderate, right? It's like moderate usefulness, 53.9%. It means, what, like I said, 46% error and 53.9% due to regression, deviation due to regression. So that's like moderate usefulness. Okay, so here's what we'll do. We definitely didn't finish what we need for exam 3. So I posted, there's one more My Stat Lab. It's longer. You can do the first half now. And so I do the first half for Wednesday. Do the first half for Wednesday. And then the second half will be due, all of it's due Sunday night. But do the first half. Do this part of it. Knock this out. And then Wednesday's class will be a lot better for you if you've thought about worked on this. So what we'll do is we'll finish the material Wednesday. We'll review for exam 3 Monday. Exam 3 will be next Wednesday.